All right, so today we're going on a bit of a special tour. We're not walking through a museum or anything like that. Instead, we're stepping into a digital laboratory, a place where the future of computing is being sketched out, one wild experiment at a time. We're going to dive into the Theremin Q Examples repository, which is basically a quantum sandbox.
So what do you even find in a place like this? Is it just a bunch of code? Well, kinda, but it's so much more. It's this incredible mix of hardcore testing, really groundbreaking algorithms, and some ideas that are, well, they're wonderfully weird, pushing the absolute boundaries of what we think is possible with physics. So let's check out the itinerary.
So here's our game plan. We've got 5 main stops. First, we'll get a lay of the land of the sandbox. Then we'll hit the proving grounds to see how they kick the tires on these systems. After that, we'll see how they tackle some seriously tough problems. Then we'll go explore the quantum fringe, that's the fun stuff. And finally, we'll meet the team and the tools behind it all.
Okay, first stop. Let's get a look at the whole landscape. This isn't just some random pile of files, you know? It's a really carefully put together collection of experiments, and they're all designed to test, to develop, and to just push the limits of the Theremin Q quantum computing platform.
Think of this slide as the map of the entire lab. You can see right away you've got your benchmarks area for performance testing. You've got these famous quantum algorithms like VQE. There's even a section for trying to run Shor's factoring algorithm when things are noisy, which is, much more like the real world. But then you see folders named Positron and QKeco. And trust me, that's where things start to get really, really interesting.
Let's move on to our next stop, the proving grounds. See, before you can do any of the really cool, fancy stuff, you have to know if your basic tools actually work. And not just work, but work well. This is where all the core parts get put through their paces.
And here's the thing, it's not enough to just get an answer. Speed and accuracy are everything. In the quantum world, you're constantly fighting against errors or noise. It's like trying to hear a whisper in a hurricane. So the high-performance computing scripts in here are all about stress testing the system, pushing it till it breaks just to see how strong it is.
Now, a key tool they use for the stress testing is something called the Ising model. I know, the name sounds a little intimidating, but just think of it like a standardized obstacle course for quantum computers. It's a classic physics problem that's so well understood that if your simulator can solve it correctly, you know you're on the right track.
And they don't just run this test once. Oh no, they run a ton of different variations, using different software, even testing it against different types of hardware. They even take the same core ideas and apply them to unbelievably ambitious things, like trying to map out how proteins fold. That's a huge deal.
Okay, so we've seen how they test the platform. Now let's go to the wing of the lab where they actually put all that power to work. This is where they aim these quantum algorithms at problems that are just, well, they're practically impossible for our normal classical computers to solve.
And this right here shows you the potential. I mean, we are talking about the heavy hitters of the quantum world. You've got Shor's algorithm for factoring, which could totally change cryptography. You've got HHL for solving ridiculously complex equations, QAOA for optimization, and VQE, which is a real game changer for chemistry and creating new materials.
Let's just zoom in on VQE for a second, because it pops up a lot. It's this really clever hybrid idea. It's like a tag team. The quantum computer makes a really good guess, and then a classical computer checks its work and tells it how to make an even better guess next time. That little back and forth is perfect for finding the lowest energy state of a molecule, which is absolutely critical for things like drug discovery. But, it's not always smooth sailing. One of the biggest roadblocks in quantum machine learning right now is this thing called the Barron Plateau. Just imagine, you're training an AI to find the lowest point in a valley, right? But the landscape is almost totally flat. The algorithm has no idea which way is downhill, so it just gets stuck. It stops learning.
And this is where the real experimentation comes in. There's this one project, VQE QML Dissipate, that's testing a fascinating solution. What if you intentionally introduce a little bit of controlled energy loss, dissipation, into the system? The theory is that this might help the algorithm feel the slope again, giving it a little nudge so it can avoid the plateau and keep on learning. Super clever stuff. All right, let's head to my absolute favorite part of the tour, the quantum fringe. This is the what-if department. This is the corner of the lab where the projects are less about solving a problem today and more about just exploring the completely wild, mind-bending nature of quantum mechanics itself.
And you just can't make this up. One of the experiments in here is literally codenamed Positron.
and the description says it was inspired by the movie Tenet. It's actually trying to simulate anti-qubits. It's just the perfect example of how sometimes science fiction can spark real, honest-to-goodness scientific research. And then you've got the Kecho project. Okay, buckle up for this name. It uses something called out-of-time order correlators, or OTOCs. That is a mouthful, but here's the simple version. It's a tool physicists use to measure how information gets all scrambled up in a chaotic quantum system. Think about it like measuring exactly how fast milk spreads out in your coffee, but for quantum information. It's how they study quantum chaos. Okay, for our final stop, let's pull back the curtain a little bit. Let's look at the tools they're using and, maybe more importantly, the people who are actually building this incredible sandbox. Because at the end of the day, code doesn't write itself. So if you glance at the languages being used, you see some things you'd expect. Python, Jupyter Notebooks. Yeah, that makes sense for science. But wait a second. HTML? A massive 87%? What's that all about? Well, it tells you they're putting a huge emphasis on building user interfaces and ways to visualize the data. They want to make the results from these crazy experiments something a human can actually look at and understand. And of course, technology is always about people. It's so important to give credit where it's due, and this repository does. It gives a shout out to the creators of the core platforms everything here is built on. Dan Serrano for the QX simulator, Jerome Bador for Bonsai, and of course, Arjen Blau for Theremin Q itself. These are the architects of the lab we've just toured. So, as we wrap up our tour, here's the big takeaway. A place like this repository, it's so much more than just a folder full of code. It's a living, breathing laboratory. It's a place where the future is being built, where it's being tested, and where it's being imagined, right at the very edge of what we know. It really gets you thinking, doesn't it? So, I'll leave you with this question. If someone handed you the keys to this quantum sandbox, with all these tools and all these crazy experiments at your fingertips, what would you do? What problem would you try to solve? The sandbox is open. What would you build?